Welcome to another video. In this video, what we're going to look at are electric field and force examples. Okay, there's quite a few we're going to go through today. So let's just go ahead and get started. This one asks, determine the magnitude and direction of the electric force on the electron. Which gives us the charge. I'll talk about what that means, but it's minus E, of a hydrogen atom exerted by the single proton, Q equals plus E, that is the atom's nucleus. And we have an average distance that it tells us to assume here, because orbits of an electron are not constant, right? But they tell us there's an average distance here. And so we'll be using that, 0.53 times 10 to the minus 10. So we're not really given a picture or anything, so it's always a good idea if you're given a problem with no picture to just go ahead and draw it anyway, even if you don't need it, because it could end up being useful later on. So I'm just drawing, this represents, this dotted line represents the orbit. Here's the proton that represents the hydrogen atom's nucleus right here. And here's the electron that represents the orbit around it. Okay, so this electron's just orbiting. Here's the distance, r, in between the proton and the electron. And so what this wants us to find, we need to determine the magnitude and direction of the electric force. We need magnitude and direction. So if you remember from the previous lecture, the electric force is equal to this K constant, the Coulombic constant, times Q1, Q2, all over the distance between them squared, times this r vector that tells us the direction of the force. Okay, this very generic unit vector. So before we get into plugging things in and worrying about direction, let's look at what this is asking again. So it's asking for the magnitude and direction. So in most of these examples and most of the questions you'll get, we'll be able to handle these things separately, okay? Because dealing with the unit vector and all of that can be a pain. But for this example, it's actually kind of easy. So let's go ahead and get just our magnitude first. So if you remember, magnitude is basically the same thing as just like absolute value bars. It's some always positive number. And so if we get that, we don't actually need to worry about this unit vector. And so we can just reduce our formula to this, K, Q, 1, Q2 over R12 squared, okay? Where this is, R1 and R2. So all we need to do then to figure out the magnitude is just start plugging stuff in. It's okay, if you remember, was equal to 9 times 10 to the 9th Newton meter squared over Coulomb squared. Q1, it tells us, and we can treat either one of these as 1 and 2, it doesn't matter. Let's just make Q1 the electron. So it says minus E. So Q1 is actually equal to minus E, which is minus 1.6 times 10 to the minus 19 coulombs. So E refers to the charge of an electron. And then the proton, it tells us, is plus E. So Q2 equals plus E. So 1.6 times 10 to the minus 19 coulombs. Okay. And so we just have R left, which is this value. So if we plug in all of that, so we write F12 magnitude equals 9 times 10 to the 9th Newton meter squared per Coulomb squared. And then we multiply that times our two charges. And then it was 0.53 times 10 to the minus 10 meters, okay? And this guy's squared. You'll notice that the meters will square here for the units, and the Coulomb squared will cancel, giving us units of newtons, which is a force. And this actually equals 8.2, if you plug this in, 8.2 times 10 to the minus 10 newtons. So that's the magnitude of the force. That answers the magnitude. So magnitude, check. We're done with that. So now we need to figure out direction. And because there's a couple things that prevent us from giving, whatever. There's an orbit of an electron around the proton, right? So the direction of the force is changing depending on where the electron is at. It doesn't really tell us. But we can give a very generic answer because it's a very generic question. I mean, we won't really have to do anything with the unit vector. So one thing you may have noticed is when I was going ahead and I was calculating all this, I left off this negative sign, right? And that's because we're looking at the magnitude of that. And if we're looking at the magnitude, that's basically the equivalent of just absolute value bars around this whole thing, giving us positive thing, giving us positive value, positive magnitude. But what does that minus sign actually mean? So the minus sign actually means, so if we're looking at direction, and we have a minus sign, so we have a plus, and here's our number line. Okay, so this is some number line, where going in this direction is positive, and then going this way is negative. And we have our electron right here. The negative sign actually refers to this direction, because just like in Physics 1, it's very important what your origin is and what your coordinate system is. So when you're looking at signs and what they mean, they're relative, so signs are relative to the coordinate system you establish. Okay? And so that's kind of, or is inherently established, right? So if you don't establish an origin system, it's usually just your typical Cartesian system with in this case, the proton at the very center, at the origin. And so this can be kind of confusing because you get a negative sign and you're like, okay, the direction is negative. What does that mean? Or my force is negative. What does it mean? In this case, it just means this, that it's moving, the electron is moving towards the proton. Okay? So this is, negative sign means toward proton, based on that number line argument. But there's an easier way to do this sort of thing, and this is why I like to do it this second way. So way number 2 to do this. Step 1, look at charges involved. Okay, and there's 3 possibilities. There's positive and positive, positive and negative, and C, there's going to be 2 negatives. Okay, these guys will repel. These guys will attract together. So boom, boom. These guys will attract, and these guys will also repel. Okay, so opposites, right? That's where opposites attract come from, or at least, not really, but yeah, opposites do attract. So this right here is how you can tell direction. And you'll be seeing me use this in future problems over this, over way number 1. Okay, way number 2 is the way that I use. I think this is easier. So to figure out direction, ignore signs of charges and look, so ignore signs of charges and look at what charges are present, okay? And then do the like, and then do attract, repel, okay? I think that is much easier than looking at this because you can get confused with the coordinate system. Now, this is the mathematical way to do it. This is when you're just looking at the numbers, but you need to know what your negative sign means if you're going to do it this way. Okay, so either way, generically, the direction is towards the proton. So how this will be listed on exams and stuff, I will write magnitude, I'll write magnitude, comma, direction, or maybe I won't have the comma, but I'll usually just have magnitude then direction. So in this instance, I would write 8.2 times 10 to the minus, I cannot write, 8.2 times 10 to the minus 8, and then I'll write toward proton. Okay. Yeah. So as long as your answer has some sort of indication of what you're going for, should be good. All right. I hope that makes sense. Let's do the next example. And you'll kind of see that a lot of these problems are like the actual calculation of the force is just kind of plugging in and making sure you get your scientific notation right in your calculator. I do recommend being extremely careful on that. You can make a mistake. So, 3 charged particles for this example are arranged on a line as shown. Calculate the net electrostatic force on charge Q3 due to the other 2 charges Q1 and Q2. So this is the setup, and this will be given to you, okay? I'm going to actually, I think what I'm going to do is I'm going to start adding some colors here to make this a little easier. Okay. So I'm going to make the negative blue and then the positive red. And I'll still use my other pen as well. They're arranged on a line as shown. Okay. .20 meters, 0.30 meters. Okay. This guy is Q1, and it is equal to minus 8 microcoulombs. Okay, so 10 to the minus 6, right? 10 to the minus 6 coulombs right there. This is minus 4, just making sure. Microcoulombs. So again, 10 to the minus 6 coulombs. And then the red one is 3 microcoulombs. And this is 10 to the minus 6 coulombs. Okay, so 3 times 10 to the 6, or negative 6. And yeah. Here, I'll make this a little less confusion. Okay. So all right, remember, units microcoulombs equals 10 to the minus 6 coulombs. Okay. So we want the net electrostatic force on charge Q3. Oh, I forgot to write. Sorry. Okay. So we need the force on this guy on the end. Now, if you're looking at this, the coordinate system would be, so first, I think doing this is a useful coordinate system for this setup. So I'm putting Q1 at origin. And to the right is positive. Okay, so we want the net force on Q3. So if you look at, because we want the net force on Q3, we look at our thing right here. This is Q3. Now Q3 is going to be attracted to Q2, aka the force will be on the left, and will be repelled by Q1 because they're both negative. So my advice for multiple charges, set up a free body diagram, if you remember that, right? So a free body, here's Q3, here's Q3. We have the force due to the positive charge. It's attracted to the positive charge, right? Here's Q3. It's attracted to this charge, and then it's going to be repelled by Q1. Okay? So this is the force on 3 by 2. This is the force on 3 by 1. And so F net equals F32 plus F31. Okay? Which will ultimately, because to the right is positive, be the difference in these two. So it will be F31 minus F32. Okay? Without the vector signs, okay? Because we're assigning it right now. So we need to calculate F31 and F32. So F31 equals K Q1 Q3 over R13 squared. This is 9 times 10 to the 9 Newton meter squared, Coulomb squared. And then our charges. The first one, I believe, was 4 times 10 to the minus 6 coulombs. Okay, so it was 4 microcoulombs, right? The next one was 8 times 10 to the minus 6 coulombs. Okay, so we're just plugging in here. Oh, I listed 3, sorry. Q3, my bad. You can do these in any order, it doesn't matter, because you're multiplying them, and you don't care about sign. Because we already took care of sign right here. Again, you can do it that other way where you mathematically determine the sign, right? And then 0.5 meters in between them squared. So let's look at this. So Q1 and Q3, it's all the way up here. Here's Q3, here's Q1. And they are 0.5, right? Because they're 0.3 plus 0.2 squared. Right? Yeah. And it was 4 and 8. Awesome. So this, you multiply this out, what do you end up getting? 1.2 newtons. And again, this is repel. So it will be positive for repel, because we said to the right was positive. Okay, the next one we need to do is F32, which is K Q3 Q2 over R1 R32 squared. So this is going to be 9 times 10 to the 9, okay, Newton meter squared coulomb squared. Q3 again is 10 to the minus 6 coulombs, and then Q2 is 3 microcoulombs, so 3 times 10 to the minus 6 coulombs, and this is over whatever their distance is, 0.2. So you plug in those numbers, and you get 2.7 newtons attracts. And you can also say, and remember I said attract because I did it up here, right? You can also say, or negative 2.7 newtons, okay? And that's because it attracts. Now, if you were to, again, quote-unquote, brute force it with just the math, this gives you your negative value right here, your Q3, because it's a negative value. And so that's where the negative would come from. But you need to know what your negative sign means, which is why I prefer to do it the way I just did it, okay, where I just don't worry about sign at all. I do it later, or I do it with this FNet stuff. You can do it either way. Here, just to confirm, both of these were negative, which yields a positive answer, which is right here, positive for repel. So now we just need to go ahead and plug all this in. Fnet equals F31 minus F32. F31 was 1.2 newtons. And this is going to be our negative sign right here, so 2.7 newtons. And it's a answer of 1.5 newtons negative, which is, or 1.5 newtons attracts, okay? Or 1.5 newtons to the left, okay? And if you remember I hat, J hat to use direction, you can also write 1.5 newtons, negative x hat, or negative I hat if you wanted to use unit vectors to denote that, okay? There's multiple ways to talk about direction. You could say it's attractive, you could say to the left. This is probably what I'll put on an exam, because we'll have an already established coordinate system there. So yeah, just be careful with signs. Okay. Now we're going to do a two-dimensional example here. So example 3. Oh, and I should mention, just echoing what I talked about before, this type of thing where I set up a free body diagram, again, I wouldn't be, too afraid of these problems or too worried about this stuff. It's really just, you're essentially pushing a charge, right? It's like I'm pushing a box back and forth, and you have two people pushing a box. They just happen to be pushing in other directions. Again, the only thing that really changes with these problems is the type of force you're using. And in this case, we're using the electrostatic force. But in principle, it's no different than me just pushing stuff, right? So it's physics 1 again. It's forces, right? Which was unit 2 of physics 1. At least with the way I teach it. So here's example 3, and this will be a two-dimensional problem now. And we want to calculate the net electrostatic force on Q3 as shown due to the charges Q1 and Q2. So here I'm going to draw it. This is Q3. This equals, oh, this is a positive charge, sorry. positive charge down here. There's a negative charge over here. Okay. So we're just gonna finish this out. This is meant to be a right triangle. Okay. With this 90 degrees, this 30 degrees. So it's a 30, 60, 90 triangle. Okay. We want to calculate the net force on Q3 shown due to the charges Q1 and Q2. So first, I'm going to do the coordinate system. First coordinate system will be, let's do this, plus x plus y, okay, because we're now introducing a second dimension. So it's our typical system. I'm going to set the origin at Q2. All right, so we want to calculate the net force on Q3. Okay, so we want net force on Q3. So let's do the free body diagram. So here's Q3. And we've got two forces. We've got Q2, which is repelling it because they're like charges. We've got Q1 that's attracting it. So it will look like this. This is F on 3 by 2, actually. I think that was charge 2. Yeah, on 3 by 2. And then you've got this second charge down here, which is 1, and that's going to be attractive. So here, let me move this out of the way real quick. And this will be F on 3 by 1. Okay. The angle of this, alternate interior angles are congruent, so this will be 30 degrees if we want to do it this way. Okay, so now we've got our stuff. We need to calculate what these forces are, and we need to do it in the x and y direction. So some net force F on 3, okay? Let's call it F net 3. This will split up into the F net 3 in the x direction and F net 3 in the y direction, right? Because we're going to have some overall net vector. I don't know what the direction is yet. We just have these two forces. I would say Q2 is closer than closer to the charge than Q1 is, so it should have more of an effect. Oh, I forgot to put up the distances, sorry. These would be given to you. So 30 centimeters, 60 centimeters, and 52 centimeters. Sorry about that. Okay. So those would be given to you. So I don't know what the overall force would be. My guess is in the first quadrant, again, because this prevailing force, F32, should be it, because the R matters more than the charge itself, because it's squared. So it has a greater effect on the force than the actual charges do. So we need to figure out what Fnet 3x is and Fnet 3y is. So Fnet 3x is going to be F net 3, 1 in the x direction plus F net 3, 2 in the x direction, right? These forces right here, we need the x component of these two forces, right? So remember that. So you have a force, some generic force, or some generic vector, we'll just call it a force, okay? And it has an x component and a y component, okay? And we need those. We also need F net 3y, okay? So the net y component on 3, and that's composed of F net 3, 1y plus F net 3, 2y. Okay, so the force on 3 by 1 in the y direction, force on charge 3 by charge 2 in the y direction. Okay, so let's go ahead, let's start with x direction. So this is the force on 3 by 1, it's this guy. So let's first let's get F31. So F31 equals K Q3 Q1 over R31 squared. 9 times 10 to the 9th Newton meter squared Coulomb squared times our charges, which will be 6.5 times 10 to the minus 5 Coulomb. And then the second one, sorry, I've got to write it down here, 8.6 times 10 to the minus 5. Here, let's just do this. I've got infinite space, so not infinite probably, but a decent amount. So 6.5, then 5 times 10 to the minus 5 coulombs, okay? And now the distance between them is 60 centimeters, because we're going between that charges 3 and 1. So 60 centimeters is converted into meters, okay? So make sure to use meters. Okay, so you calculate this, you do the math on this, and again, I didn't use signs or anything, we just want the magnitude. F31 is equal to 140 newtons, okay? Now we need x and y component, okay? Oh, I was just doing the x is first. Yeah, we can just, that's fine. Let's just do the x's. Okay, so now we need the x component. So F31 is 140 newtons. F31 is this vector. So let's look at this vector. So this is F31, okay? And this is our angle, 30 degrees. Now, this right here is our x component, and this right here is our y component. So the x component, F31x, equals cosine of this angle, because if you were to flip this over, this is a much more typical setup, right? Where this is F31x. It's the adjacent side, okay? So we just do F31 times cosine of 30 degrees equals F31x, okay? And then we'll do the y later on. So 140 newtons times cosine of 30 degrees equals 120 newtons. Great. Now we need to do F32. Okay, so we're finishing off the x's, because I just decided to do it that way first. You can do however you want, really. You can do both the x's. Why can't I zoom? Okay. So F32 then will be K Q3 Q2 over R32 squared. You plug in all those values, which is going to be 9 times 10 to the 9th. I'm going to skip units. Skip units. 5 times 10 to the minus 5 coulombs over 0.3 meters. Again, make sure you use you convert to meters. And this gives us 325 newtons. Okay, so now let's go back and look at F32. So F32 is this guy, points up straight. There's no angle. So F32 is all in the y direction. So if a vector is all in the y direction, then F32x equals 0. You can also see this by just doing F32 cosine of 90 degrees, which is what this would be if it's in the y direction. And this would equal 0, if you didn't realize that fact. So F3 net x then equals F31 x plus F32x equals our first vector right here, 120 newtons, plus 0. So this is just 120 newtons. Now we need the y components. Okay. So if we look at this, we already have F31, which was 140 newtons. So we just need sine of that angle, right? So if we go back to this, opposite side is the y component, okay? Right, so we had this guy, this is 30 degrees, here's our y. This is the opposite side to this angle. So we need 140 newtons sine 30 degrees. And sine of 130 is actually 1/2, so this is 70 newtons. Okay. Now, if I'm looking at this, the y component points down. Right, let's go back and look at this. Here it is. It's beneath the x-axis. It has a negative y component. So F31y equals negative 70 newtons. Points down. Okay, now let's look at this other component here. This guy was pointing straight up, so it's all in the y. So F32y actually equals F32, which equals 325 newtons. Just making sure. Yeah. So F3 net y then equals 325 newtons minus 70 newtons. So we're just adding those two components, right? Because this was F31y. This was F32y. This was F31y. And we end up getting 255 newtons. So now we have our two components of the force on on Q3, sorry, which is F3x and F3y, or net. I think I was using to call them that. Let's stick with that. F3 net x and F3 net y. So we have 255 and 120. So 120 newtons. So that's what this looks like, given our coordinate system, where this is positive x and this is positive y. We have, let me use just some other color here. That's terrible. Let's use this. So this is 120 newtons positive, and this is 255 newtons. And so this right here will be our overall. This will be F net. Okay, this was F net x. This was F net y. Then this will be our angle. So we still need to get F net. Oh, and I was right. It will be in the first quadrant. So will be. So when we look for theta, we should be looking from 0 to 90. So theta equals 0 to 90 degrees. Okay. So F net, if you guys remember, we're using Pythagorean theorem, so this will be F net, F3 net x. There's a 3 here, sorry. Squared plus F3 net y squared. This will be 120 newtons squared plus 255 newtons squared, square root. And this will be 280 newtons. This is F3 net, the magnitude. And this will be 280 newtons, okay? Direction, if you guys remember how to do direction, it's theta equals the arctangent of F3 net x, the x components, over the y components. And so theta equals 255 newtons over 120 newtons. The newtons cancel, giving us unitless. And this is the arctan of that, sorry. And this equals 65 degrees. Again, make sure your calculator is in degree mode. Okay. So these types of problems, you probably started noticing it's all about vectors. Make sure to brush up on vectors if you're struggling. And there's some vector stuff to help you catch up on that if you haven't had Physics 1 in a while, or something like that, okay? So to put this all together, F3, the force on 3, or the net force on 3, whatever we're calling it, was 280 newtons. And direction is 65 degrees relative to the positive x axis, which was the first quadrant, okay? We were looking for something between 0 and 90, and we found it. So again, make sure you brush up on vector stuff. There's stuff attached to the course that you can look at, okay? All right, let's do the next example. Okay, so the next example I know that was a lot. Vector stuff, unfortunately, is always very, very long and involved. But unfortunately, both force and electric field are vectors, and there's not much that we can do to get around that. So let's look at this next one. We want to calculate the magnitude and direction of the electric field at a point P, which is 30 centimeters to the right of a point charge. Q equals -3 times 10 to the -6 coulombs. So here's the drawing for this guy. To the right of a point charge. So this guy is Q and it's negative, so I'm going to call it blue here. Q equals -3 times 10 to the -6 coulombs. And it says we want to calculate the magnitude and direction of the electric field at a point P. Okay, so here's our point P. All right. So, if you guys remember, here's our thing, 30 centimeters. The electric field equation is E equals KQ over R squared. Okay, it's the force per unit charge at some point in space. Okay, where if we were to place a charge there, that charge would experience a force that's based on the electric field. Okay, it is you know, as the electric field there increases, so too with the force on a charge placed there. Okay, so let's go ahead and do this algebra here. So we just plug in K, 9 times 10 to the 9 newtons coulomb squared per meter squared. Okay, the charge, which is -3 times 10 to the -6. I'm going to go ahead and, well, I'm going to go ahead and leave the minus, well, no, let's get rid of it. You can do it either way again, but I'll show you how to do it both ways. And then the distance was 0.3. Again, we're worried about 30 centimeters here, so 0.3 meters squared. And if you plug in the numbers on this, you'll get 3 times 10 to the 5th. So we're just looking at the magnitude. Newton per coulomb. So only 1 coulomb will cancel here. Okay, it's the force per charge. So that's why we have these units. Now, the direction, because it's a negative charge, will be inward. So direction, right? If you were to draw this charge, it has an electric field that's all pointing inward. Because it's to the right, it would be over here, so it would be to the left. So direction of E field is to the left at P. Okay? And so these are our two answers. If I had left the negative sign on there, the negative would have told us, hey, this is the origin, Q is the origin, and it's pointing to the left, because to the right is inherently positive, okay, in this setup. So, kind of a short example. Let's go ahead, so that's just a one-dimensional problem. Let's go ahead and do a one-dimensional problem now with multiple charges. So this is going to be, all right. This is going to be example 5. Okay, so example 5. 2 point charges are separated by a distance of 10 centimeters. One has a charge of negative 25 times 10 to the minus 6, and the other has a charge of 50 times 10 to the minus 6, both coulombs. We wanted to determine the direction and magnitude of the electric field at a point P between the two charges that is 2 centimeters from the negative charge. Whew, that was a mouthful. And then if the electron is placed at point P and then released, what will be its initial acceleration? Okay, so let's go ahead and draw this system out. So, whoops, Q1, I'm pressing blue, thank you. Okay, if you want to not let me switch. How weird. Maybe I need to use my mouse. Okay, whatever. We can, oh, there it goes. Kind of. Okay, whatever. Working on it. Okay, here we go. So minus 25 times 10 to the minus 6 coulombs. That's what that charge is. And it's, the other is 50. I'm just going to have to keep changing this. So this next one is 50. Times 10 to the minus 6 coulombs. And we want to determine it 2 centimeters from the negative charge. Okay, so let's do it this way. So this right here is 2 centimeters. That would make this 8, this point P, because they're a total of 8 or 10 centimeters apart. Okay, so 2 plus 8, 10. And we want the electric field at point P. We need E at point P. Okay, so let's go ahead and do this. We're going to do the same thing we did before, where E equals K. Let's call this, so this guy's Q1, and then this guy is Q2. Okay, so E1, okay, is going to be K Q1 over R, let's call this R1, R2. So 9 times 10 to the 9 Newton meter squared Coulomb squared. Q1 is the 25 times 10 to the minus 6 coulombs. Again, magnitude, but it'll be negative when we're doing the math on it. Sorry, it's squared. So that was 0.02 centimeters squared. Oops. And so if you plug all this in, you're going to get 5.6 times 10 to the 8th this is Newton per Coulomb to the left. Okay, and it's to the left because at this point, this guy has an electric field that's moving towards that point, or towards the charge. Okay, so it's to the left. We need to do E2 now, which is K Q2 over R2 squared, which is 9 times 10 to the 9 Newton meters squared per Coulomb squared. Q2 is 50 times 10 to the minus 6. And this is over 0.08 squared. 0.08 meter squared. And this is equal to 7 times 10 to the 7 Newton per Coulomb. Okay. And this will also be to the right. Okay, because, or no, wait, it's pushing outward, so it's to the left, sorry. So we have two, if you want the electric fields here. So I'll just draw it. So this is point P. We have the -1, which is pulling in. And we have the +1, which is also pushing in that direction. Okay? Because it's radiating outwards. So this would be to the left. So now E at P equals E1 plus E2 equals 5.6 times 10 to the 8th coulomb, Newton per coulomb, plus 7 times 10 to the 7 Newton per coulomb. And this is 6.3 times 10 to the 8 Newton per coulomb to the left, or, negative 6.3 times 10 to the 8 Newton per coulomb. Okay? Now, if an electron is placed at rest at P and then released, what will be its initial acceleration? Okay, so we need, so this is part B, Excel. If you remember from Physics 1, F equals ma. This would be mass of electron, because that's what we're placing there. This would be the Excel, what we need. So that's what we need. And this is the electric force. So we need to calculate that. So F equals Q times E. This would be the charge of electron. Oops. So this is charge of electron. And this is electric field that's established. So F at point P equals Q times the electric field, which we just calculated right here. Okay. The other way you can do this is you can again do, so this is, or we could use K, Q, Q over R squared for each charge. Again, just like we did on the number line example, way back here, example 2, right? It was up here. It was this guy, okay? So we would have to do all of that again. Or we can use the fact that we already used the electric field. So, or we already calculated electric field, so let's use that. So let's use F equals QE as we already have electric field. Okay, so F at point P equals minus 1.6 times, well, I'm gonna do it without the signs, okay? And then I'll show you what the signs mean. So 1.6 times 10 to the minus 19 coulombs times the electric field, which is 6.3 times 10 to the 8th. Newton per coulomb. The coulombs will cancel, we'll be left with units of newtons. And this gives us 1 times 10 to the minus 10 newtons, okay? So this is magnitude, okay? Now, if we were to plug in the signs, we'd have negative and negative, which would yield positive, which means if you place an electron, so here's the E field, so what signs mean, okay, you have an E field that's moving, whoops, you have an E field that's like this, so this is E, and you're placing an electron in this, it will move to the right, okay? It will move opposite of E field. A proton or something with a positive charge would move with it, okay? So, and that's due to both having negative signs, okay, mathematically. But again, you can just look at it and see why it's like that as well, okay? We can reason it just by looking at it and saying, or just by using these signs, really. Okay, so now we have the magnitude and direction. So the electron will accelerate to the right, okay? But let's get the acceleration. So we have force, still need accel, okay? So F equals ma, okay? And so F here is 1, or let's do it this way, A equals F over m. So F was 1 times 10 to the minus 10 Newton, sorry, and m is 9.11 times 10 to the minus 31 kilograms, okay? So this is the mass of an electron. And you won't need to memorize, okay? Won't need to memorize that. So you do the math on this. A equals 1.1 times 10 to the 20 meters per second squared, okay? Is the unit you get when you get a Newton over a kilogram. And this is to the right, okay? That's because electrons move opposite to E fields. Okay, so electrons and again, you can figure that out with the signs. Another explanation for this will come when we talk about energy. So another which you'll learn right after this, okay? When we do electrical energy. Okay, so that's this example. So let's just real quick go back over what we did. So this was a lot, right? All of this entire thing was written, okay? But it boiled down to most of this was just draw the problem. Okay, so you have Q1 and Q2, they're separated. We wanted to figure out the electric field at that point. Q1 has a negative electric field, so it would produce a field to the left. Q2 has a positive field, and because the point's out here, it would push that way as well. So both parts of the E field were to the left. So we did KQ over R squared for both of them and added them together. And that gave us the net electric field. Then all we needed to do was figure out the acceleration of the electron, but we needed the force, okay? So the force was equal to QE, and again, you can also use the KQQ over R squared, but you'd have to do that twice, okay? With Q1 being any of these charges, these two charges, and Q2 being an electron there, okay? And that would have been a lot more work to do that again. But since we had the electric field, we could just use QE. So doing that with QE, we get this magnitude. Then we divide that, okay, so then we have the force, now we just need to divide it by the mass of the electron. That gave us the acceleration. Next up was figuring out the direction of the acceleration, which if you actually look at this QE equation, Q would be negative, the electric field was negative, that yields a positive electric field, which in our coordinate system would push it to the right. Now, again, I'll give you another argument conceptually about why this is the case when we do energy, and it will make a little bit more sense, I think. But typically, and I mean typically always, an electric field will move opposite to the electric field it's placed in, okay? So let's, yeah, that's that example. So let's do this next example. So we've got example 6 now. Okay. And for this example, we want to calculate, it's a very short question because it's giving you the picture. So we want to calculate the total electric field at point A as shown. Okay. So let's go ahead and draw this. Okay. Here's Q2, 50 microcoulombs. Here is Q1, which is minus 50 microcoulombs. Here's the point A. And here's the rest of the problem. Okay. So this is again a 30, 60, 90 triangle. It's my favorite because it's easier to just work with those particular angles, allowing you to focus on the actual work. And if you notice, this is identical to the force example that we did, but now we're finding an electric field. Okay. So let's look at this. E at point A, so the electric field at A will be due to the electric field due to charge 2, which will push upward, and Q1, so charge 1 and charge 2, and charge 2 would do it like this. So EA is equal to E due to Q2 plus E to Q1. And if you look at the free body diagram here, so this would be EQ2, then EQ1 would point like this. Okay, this is the F. It's not really a free body diagram because it's not a force, but this is just what point A looks like. So E fields at point A, that's what these guys look like. And so we need to get those guys known, okay? So we need EQ2x, EQ2y, EQ1x, EQ1y. Sorry, it's a mouthful. Okay. EQ1 has both of them because they're diagonal. EQ2 doesn't have an x, so this guy will be 0 because it's only got a y component. So let's go ahead and figure this out. So EQ2y equals EQ2 equals K Q2 over R2 squared, whatever you want to call it. That's 30 centimeters. So 9 times 10 to the 9 times Q2, which is 50 microcoulombs. 50 times 10 to the minus 6. There you go. Coulombs. Over the distance, 30 centimeters. 0.3 meters squared. This guy ends up being 5 times 10 to the 6 Newton per coulomb. Okay. Again, EQ2x is 0. We don't need to worry about that. Let's do EQ1x. Or actually, let's just calculate EQ1 first. So this will be K Q1 over R1 squared equals 9 times 10 to the 9 times Q1 minus 50. We're just going to do the magnitude. Over R1, so the distance, 60 centimeters. So 0.6 meters squared. You plug that in, you get 1.25, sorry, times 10 to the 6 Newton per coulomb. Okay, so now EQ1x equals EQ1 cosine theta, and that will be 30 degrees. And it will be positive because it's going to be, so EQ1x, again, it looks like this. This is our x, this is our y. So we're going to use cosine. So 1.25, whoops, times 10 to the 6 Newton per coulomb, cosine 30 degrees. This guy equals 1.1 times 10 to the 6 Newton per coulomb, and then EQ1y equals 1.25 times 10 to the 6 Newton per coulomb, sine 30 degrees equals 6.25 times 10 to the 5th Newton per coulomb, and it's negative points down. Okay. Just like before, just like with the force. So E at point A will be the square root of the x components. Oh, we need to figure that out, sorry. The x components and the y components, we need to finish those. So total x will be EQ2x plus EQ1x equals, there's only one x component. The total y is going to be 1.25. Oh, sorry. This EQ2y plus EQ1y. EQ2y was 5 times 10 to the 6 minus the 6.25 times 10 to the 5th. And this ends up getting us 4.4 times 10 to the 6 Newton per coulomb. Okay, so here's our total x, total y. So E at A equals EX squared plus EY squared, the electric field x component squared plus the y component of the electric field squared. And that would be 1.1 times 10 to the 6 Newton per coulomb squared plus the 4.5 or 4.4, sorry, times 10 to the 6 Newton per Coulomb squared. And what we end up getting is 4.5 times 10 to the 6 Newton per Coulomb. So this is the net E field. Okay, we still need the direction. So theta equals the arctan of the x over the y, which is the arctan of, or the y over the x, sorry about that, going crazy, which is the 4.4 times 10 to the 6 over the 1.1 times 10 to the 6, which would give us arctangent of 4, which is 76 degrees. And this is relative to plus x axis. Okay. And again, if we look at this, so that means that our E field at A is something like this. This is point A. And that's because we have some positive charge down here, which is doing this. And then we've got some other charge that's doing this, but this is much closer. So it has a larger effect. Okay. All right. Let's do the next one. So example 7. Find the electric field at point B. So here's our example. So you got Q2, this equals 50 microcoulombs. You've got Q1 minus 50 microcoulombs. And then you've got this not really intricate, kind of intricate setup here. This is 30 centimeter. This is 40. This is 40. And these are both 26. And these are the same angle theta, which would be 30 degrees, I believe. Okay. So, all right. Sorry about that. You're actually not told theta. Okay. Let's go ahead and see if we can work around that. We have all the lengths of the sides, right? So it shouldn't be an issue. But let's look at this. So, oh, and here's point B. This is B. Okay. So at point B, let's look at what's going on. At point B, here's point B. Okay. We've got this guy who's producing an electric field that points this way. And then you've got this guy that's producing an electric field that goes this way. Now, they're equal distances from the point, right? They're both 40 centimeters, so they are both same charge and same distance. And what happens is, check this out. You've got these components. So the components should then be the same. In other words, whoops, they're not both Q2. This guy was Q1. Sorry, here, let me just do that. Okay, so this means that EQ2 equals EQ1, the magnitude, okay, is the same. EQ2x equals EQ1x. And the y's are also true. But if you check this out, one's pointing up and one's pointing down. So the y's point in opposite directions. And thus cancel. So we don't need to calculate the y. At all. Okay, we don't need to worry about that. And the x components are the same, so we only need to calculate one x component and then multiply by 2 because they're the same, right? So this is an example of a problem with symmetry. If you see this, use symmetry to your advantage, okay? Don't do more work than you need to, especially during exams when I purposely set up symmetric situations for you to exploit, okay? So let's go ahead and just do the math on this, okay? Let's just do EQ1, doesn't really matter. KQ1 over R squared. This would be 9 times 10 to the 9th. 50 microcoulombs, 0.4 meters squared. Sorry, this would be 10 to the minus 6. I'll just write it like that. And this would be 2.8 times 10 to the 6 Newton per coulomb. Okay, so we need x component. So EQ1x equals 2.8 times 10 to the 6 Newton per coulomb times cosine of theta. But we don't have theta. But instead, we have what theta is equal, or what cosine of theta is equal to. We have all these sides, right? So if you're looking at this, the adjacent side, the opposite side, cosine of theta equals the adjacent over hypotenuse. So that's all we really need to do here. So we plug in 2.8 times 10 to the 6 Newton per coulomb. Then we plug in the adjacent over the hypotenuse side. And so this equals 26 centimeters over 40 centimeters, or you could do 0.6 and 0.4 if you want to have them be in meters. It doesn't matter because the units cancel. And this equals 3.6 times 10 to the 6 Newton per coulomb. Okay, so this is from one charge. So we need to do 2 times 3.6 times 10 to the 6, and we get 7.2. Oh, wait, sorry. I did it in one go before, so sorry about that. So we have this set up, and then we need to multiply it by 2. Okay? And so this is for both charges. And this was, again, the 4x component. And this was E from 1 charge. Okay, so you multiply all that, and you get 3.6 times 10 to the 6 Newton per coulomb. Direction is just plus x, or 0 degrees relative to plus x axis. Okay, and that's the case because, again, this is perfectly symmetric, and it looks like this. It would just push just to the right. Okay, if they were different distances or different charges, it wouldn't be that way. All right. So let's go ahead and just let's go ahead and do one more example. All right. Here it is. Here's the final example. What is the electric field between the 2-point charges Q1 equals 2Q that are a distance x apart? So this is kind of like a fun problem I usually like to just do. We don't really know anything about these charges. We just know they're a distance x apart. Oops. And we don't even know their charge. We don't even know if they're positive or negative. We just know it's a distance x apart. Okay? And we want to know, where's the electric field 0? E equals 0 at what point? So let's go ahead and look at this. If we know that at some point between these two, we're told that it's 0, right? And so if it's 0 at any point, that means that E at some point due to charge 1 will be equal to 0. And we know that EQ2 at some point will be equal to 0 because we're told that, right? We're finding the point at which that's the case. So if they're equal to 0, they can be equal to each other. Okay? Because they both equal 0. And so we can actually write in K Q1 over the distance squared equals K Q2 over the distance squared. Now these are the distances, right? This is, if we redraw this, Q1, Q2, there's some point where this is R1 and this is R2 where E equals 0. But we don't know either of these. Okay? We only know that the total distance is x. So if the total distance is x and the distance to 1, we can just call it r, then this would be the total distance x minus r, right? Because the total distance is x and we've already taken up some generic r, so that means that the second one would just be x minus r. So we can actually go ahead and just do that. So let's say the first distance is just r, then the second distance must be x minus r. So now we're solving for r. Just need to solve for r. Okay. So k is the same. We can cancel k. So now we've got this r squared and then q2. And I'm going to go ahead and expand this. So it'd be q1 r squared equals q2 over x squared. So multiply x minus r minus 2xr plus r squared is one way to do this. Okay. Actually, I think for this guy, because the r's are going to be coupled together, I think it's easier if we just leave it in there for now. Okay. Oh, we're told q1 equals q2. So q1 equals q2. So we can cancel those two. So now we're left with 1 over r squared equals 1 over x minus r squared. So let's go ahead, cross multiply, get rid of the fraction. It's bothering me. So we do that. So we have x minus r squared equals r squared. And now we need to solve for r squared. So now let's expand it. I could have expanded it before, but so x squared minus 2xr plus r squared equals r squared. These two go away. So we subtract that over. R squared minus r squared is 0. So we have x squared minus 2xr equals 0. So now we can kind of pull x out. Let's pull x, or let's just say x squared equals 2xr, so add it over. Cancel an x equals 2r, or r equals x over 2. So what does this tell us? X over 2 is half the distance. So the electric field will be 0 between two charges when they are the same. So E, when charges are the same at a distance x over 2. And if you think about this, this kind of makes sense, right? So you've got a charge here and a charge here, and they're both pushing. And if they're the same charge, halfway in between, they should be 0, right? Because they will perfectly cancel. I just wanted to show you kind of a problem like that, just for kind of fun. You probably won't see too many problems like this. I just thought it was an interesting problem for you to solve. So that's pretty much it. Again, the main issue with these types of questions that you'll discover is, are you good with vectors? This is basically just straight up Unit 2 from Physics 1. So make sure if you're struggling, do well with vectors. Study the material I've posted, things like that. And of course, I can always help you as well. The only other thing at that point that you need to worry about, I guess, is direction, because the actual equations are pretty easy. You just plug in. You got to deal with scientific notation. There's no way around that. But other than that, you just have to plug into the equation and then deal with the direction based on if they're attractive or repulsive. Okay, so yeah, that's pretty much it. This video is kind of long enough, so thanks for watching, and I hope you got something out of this. So I'll see you in the next one.